Hello and welcome to my channel. In this series, I take you through past VCAA Maths Methods exam questions and provide you with my full work solutions. In today's video, we'll be going through question 6 from the 2020 exam 1, so that's the calc-free exam. As always, I'll invite you guys to attempt the question first. If you haven't done so already, you'll find a link in the video description as usual. Cool, so question 6 here reads, let the function f, which has a domain between 0 and 2, where the function f of x is the 1 on the square root of 2 of x, and we're asked to find the domain and the rule for the inverse. Cool, so there's a couple options on where you'd like to start. I'm going to start off by the very first thing, just re-expressing this function f of x. I don't quite like it in the form that it's in there. So you can see, if we just rearrange this slightly, we can bring everything underneath the square root, and we'll just have that function as the square root of x on 2, like that. Cool, a little bit nicer. Makes things a bit easier. So what are we going to do next? So to find the inverse, we know we've got to swap x's and y's essentially, but since there's no y's, we need to essentially create one. So I'm just going to say let y be equal to what f of x was previously, and then we'll say for inverse swap x and y. So almost using, a full sentence, almost. And then we can get on with the rest of the inverse process. So physically swap them, rearrange it, so square both sides, multiply both sides by 2, we'll get y is equal to 2x squared. But obviously the function, or the inverse function, f to the power of minus 1, it needs to be in terms of just x's and the standard notation. So we can't really leave it in the y since we've just created this y out of nowhere essentially. So that's the function there. We're also asked to find the domain, and it's good practice to just provide the domain whenever you're doing an inverse anyway. So we notice that, well, I guess we know from the theory that the domain of the inverse is equal to the range of the original function. So I might just write that out. So the domain of the inverse will be equal to the range of the original function f. So we know the domain of the original function f, and it's a square root function, right? And if we sort of take a sneak peek, question B here, they already show us what this original function looks like. So you can actually see that the range of the function f of x goes from 0 up to 1. And you could confirm that by subbing in x is equal to 0, we get 0, and x is equal to 2, you'll get 1. So therefore, this range for the function f is from 0 to 1, and therefore the domain for the inverse function has to be the same set of values. So let's finish this off by saying x is an element of 0 to 1. Cool. So hopefully that's nice and clear so far. Moving on to the second question, question B. So here they're providing us with the graph of that same function. It's shown on the axis below, and we're asked to sketch the inverse function over its domain, which we found, and label the endpoints and the points of intersection with the function f, giving their coordinates. So we know that any inverse function and its original function will intersect along the line y is equal to x. So if we just sort of dot that line in, it's essentially going to look something like that. So we can see that this original function f of x intersects, or it passes through the point half-half. So this is where it will actually intersect with our inverse function. So it's probably okay just to delete this line in here. You don't have to. I sort of just would do that in lightly, if anything, because it's not really asking it. It's just sort of helping us with our workings. And sometimes examiners do like to see that. So next I'm going to plot in well, I guess we know this endpoint will be the same, and since the inverse is the process of changing all the x and y values, then we know the endpoint for our inverse function should be 1, 2. So 1, 2. So I'm actually doing that as the first step, and we know the shape should be sort of like a mirror image about this line y is equal to x. So if I sort of try to plot this in as best I can, making sure it intersects at the point where we've got half-half, and that should be just about everything. So just trying to keep the shape as close to quadratic as we can there. You don't want it to be too flat at any particular point, so just do it in lightly, and try to don't rush through it, because a lot of people lose marks when they're sketching. The shape's quite important. Cool, so let's just double check we've made all the requirements. So we've got the endpoints in, pass this through the origin obviously, and we've got the point of intersection. Great, cool, easy, hopefully easy. C, find the total area of the two regions, one region bounded by the functions f and the inverse function, and the other region bounded by f, the inverse, and the line x is equal to 1, and give answer in the particular form that's expressed there, where a and b are elements of z plus, so they're positive integers. Okay, so it might help to sort of draw onto this graph, or just lightly annotate it, the areas that we're actually interested in. So first area is the region bounded by f and its inverse. So that would just be this sort of bound region there. So I'm just going to sort of label that A1. And then the next region says between the line x is equal to 1. So x is equal to 1's over here. And if we were to sort of enclose off this area, we can see it's going to be this sort of triangular looking region there. So that's our A2. Great. So now we've got them sort of labeled, we can work out each of those areas individually and then just combine them together to get the total area. So A1 would be equal to the integral between, and it spans between 0 and half the range of x values, and we've got the original function f of x is on top of the inverse. So that means I'll have f of x first and then minus its inverse. That's going to be the A1 area. Next, let's define the area A2. So we know that's defined between half up to 1. So 1 up the top, half down the bottom. And this time we've got the inverse function on the top and the original function on the bottom. So the inverse goes first, minus the original dx. Great, so that's how I've set up the two areas. And then once you evaluate those, sum them together, you'll get an answer, and then you just need to re-express it in that form. So I'm not going to go through the entire integration because it's a bit tedious, but to show you like the next step or so. So I'm just going to sub in what the actual function is. I ended up using this form for the function f of x just because I found it slightly easier to work with than some of the other forms that we had. 2x squared dx. Hopefully you guys are comfortable with the integration. Maybe I'll just do one more step. So we're going to have that 1 on the square root of 2. We can leave that separate because it's like a scalar, and the function's only the square root of x, or x to the power over half. So we just need to increase that power by 1. So half goes to 3 on 2, and divide by that new power. So 2 on 3 like that, minus x squared becomes x cubed. And again, we're dividing by the new power. So we'll have 2 on 3 is the fraction there, and then just evaluate that between half and 0, which is a little bit tedious. Just be a bit careful when you're dealing with the fractions and some of the surds that you'll have. So if you do that all correctly, the answers that I got for A1 and A2 when defined like this. For A1, I got 1 on 12. A2, I had 9 on 12 minus 2 on 3 root 2. So the total area, which is what it's asking for, AT is equal to A1 plus A2. So you can see 1 on 12 plus 9 on 12 would be 10 on 12 minus 2 on 3 root 2. But it's asked us to express the answer in this particular form here. So we notice that the denominator is just a 6. So we need to somehow make this a 6 on the bottom here as well. So the first part's okay. We know we can just half the 10 on 12, both the top and the bottom, to keep the fraction the same. So we would have 5 on 6 But what do we need to do to the top and bottom here to make that a 6? So if we multiplied it by the square root of 2, we would have 2 times root 2 is 2, 2 times 3 is 6. So we actually just need to multiply the top and the bottom by the square root of 2, just like we divided the top and the bottom of that first fraction by 2. So doing that, we'll have 2 root 2 over 6. And since they're both over the same denominator, we can combine the numerators. So we'll have 5 minus 2 root 2 like that. And if we compare it to the form that it's expressed in, this looks right here. So we see a, and then we've got minus b root b, so 2 root 2, all over 6. So I guess we've matched that form now, and if I'm just to label these variables, a would be 5, and b would be 2, obviously. Great. Hopefully that was nice and clear for you guys. Definitely give that a shot, especially, this is a typical exam where you will have to deal with some tedious numbers, so make sure you can definitely go from sort of this step, setting up the integral, to this step. That being said, it's probably only worth like 1 or 2 marks out of the total of 4 marks, because you will get easy marks by just setting up the integral correctly, and then there's probably another mark allocated to rearranging the form, but you wouldn't be able to get probably this answer unless you've done the integration steps correctly. So let's have a quick look at the examiner's report. I'll jump back to question 6a to start. So the comments read that students confidently attempted this question, however some did not use the notation well. It's a very common mistake, especially when dealing with inverses in particular. So many students left their answer in the form y is equal to 2x squared. So they were left at that step there and lost a simple mark. Thus assuming that f of x was the same as the inverse, in contradiction to their prior working. Some students did not state the required domain or expressed it incorrectly. So it sounds like the biggest one, sort of the point that they pick up on, it's really important to have the notation, because we've got y is equal to x on 2 here and y is equal to 2x squared here. So that's sort of what they're talking about in terms of contradiction. We can see that around half the students got full marks, which is good to see, but that there's a good chunk of students that only got partial marks, or none at all. Moving on to question B. Most students correctly identified the endpoint at 1, 2, which is good to see, but some students either plotted it in the incorrect position or continued the graph beyond this endpoint. Some graphs lacked curvature and became vertical as x approached 1, and the point of intersection was generally correctly obtained, but often not plotted in the correct position. So interesting to see. The comment around the shape and the lacking curvature is a point that comes up quite frequently. It's really important to pay careful attention to the shape, spending an extra few seconds to try and get that right. So you don't want to lose an easy mark or 2 because your shape's wrong or you've rushed it, whereas you could have just taken a little bit more care and got the easy mark there. Moving on to, about 70% got full marks for B, so answered pretty decently well. Question C, so only 10% of students got the full 4 marks, 18% of students got 3, and more than half, large majority of students got 2 or less for this question. So most students recognise at least one of the 2 required areas and generally attains a correct antiderivative, though often not all the correct antiderivatives required. So they would sometimes get 1 but not the other, is what it sounds like. Also makes note of the errors in evaluating definite integrals and answering in the format specified. So noting it is quite maybe a little bit challenging to get from once you've got the integral to these values. That's something that you just sort of got to do and learn through practice, and sort of manipulating it into the form. So you have to sort of see what the patterns are with the numbers that you've got and the form that you're trying to get it in. So the key thing for me when answering this is to look at the denominator being 6 and thinking, how can I get these individual components and force them to have a denominator of 6? Once you can make that connection, the rest of it comes relatively straightforward from there. Great. So that about does it for this video. If you guys found the video useful, then please give it a thumbs up and share it with any friends or classmates. If you're new to the channel, then please subscribe to my channel for more content like this in the future. Lastly, if you've got any questions that you'd like to see me answer on the channel, then please leave them in the comment section below or send me an email at yourmathquestions@gmail.com. Thanks for watching. I'll see you in the next one.